In this highlight video, we're going to start to bring together all of the reactions that we've learned this semester and use them for chemical synthesis. The goal is to be able to identify a reasonable reactant and reagents that could be used to synthesize a given molecule. So what we're trying to do is string together reactions that we've learned in this chapter and in any of the previous chapters. Let's first talk a little bit about synthetic planning. There's really two main ways to decipher or to plan syntheses. The first is to think about the synthesis in the forward direction. That would be in the synthetic or in the synthesis direction. So the problem might be something like this. How do we convert acetylene into this ketone using a sequence or series of reactions that we've learned? So trying to figure this out in the synthetic direction would be looking at the alkyne of acetylene and asking yourself, what kind of reactions can you do to modify that alkyne? We know that we have a longer carbon chain, so you might imagine that you could turn acetylene into an acetylide anion like this. And two, you could add some alkyl group onto that via a SN2 substitution. But to just look at that, we might not know how long of a carbon chain we should add. So really a better way to analyze this, unless it's very clear to us right off the bat, is to do our planning using what we call retrosynthesis. And this is really backwards planning. A chemist named E.J. Corey at Harvard University won the Nobel Prize largely for coming up with this type of synthetic planning strategy. So what this would say is that we're going to start with our product, and we're going to draw a different kind of arrow. So this is a backwards arrow, and what we're going to do is we're going to ask, what can we make this ketone from? And so far, what we know is that we can make a ketone from an alkyne by a hydration reaction. So we have really two possibilities. We could either make the ketone from this alkyne. Okay, so the alkyne would either have to be here or it would have to be here. So that would be one possibility. The other possibility would be to put the alkyne here. Now, if we have two possibilities, we have to ask ourselves which one might be better than the other. Are they both equally good? So if we think about doing our hydration reactions, so water and sulfuric acid, or we could do a hydroboration oxidation, does this give us our product? So the answer is yes, it could give us some product if the OH adds to this position. But because this alkyne is in the middle of a chain, the OH could also add to this position, and that would give us another product. So we would get a mixture of products. And so this way is not really so good. Notice on the bottom option, if the OH ends up here or at here, we get the same compound, right? The ketone at either of those places is our product. So this is a very good intermediate. From there, we can ask ourselves, what can we make this alkyne from? And so we should know that we can extend the carbon chain using acetylide anions. So we can make an acetylide anion from this terminal alkyne, add an alkyl halide, and extend the chain. We could go back even farther. We could do another acetylide anion reaction to get to here. So this would be a retrosynthesis. We could then fill in with the forward reaction. So we'd start out with sodium amide. This is our very strong base. It deprotonates the alkyne. And then we want to add an ethyl group, so we could maybe start with bromoethane. That would give us that product. We could then do exactly the same thing again and add an ethyl group onto the other side. And we could use a chloride or an iodide. That's just our own choice what we want to use as the halide. So that would give us this symmetrical internal alkyne. And then from there we know that we could either use water and sulfuric acid, or we could do a hydroboration oxidation. Either of those would be equally just as good. All right, so sometimes it's easiest to figure out problems like this in a retrosynthetic manner. So when we start thinking about synthesis, we often break it into two different parts, just like we had in this problem above. The first part in the synthesis is usually going to be to build the carbon framework. Okay, so that would be the first part here in the forward direction, starting with the alkyne, extending it and extending it again, right? This is building up the carbon framework. And the second part is going to be to manipulate the functional groups. So that part of it is where we convert the alkyne into the ketone. Many of the synthesis problems that we will be involved with will have these two parts to the synthesis. How do we build up a carbon framework? In order to do that, we need to be able to make carbon-carbon bonds. And we've seen so far only two ways to do this. Both involve SN2 substitutions. The first way that I have listed here is to do an SN2 substitution between an alkyl halide and cyanide. So this is just a substitution. This would go here, this would come off, and we would get, this is called a nitrile. All right, we were able to add one carbon, and we have a functional group that we don't know what to do with yet. And so we have built up a slightly bigger carbon chain, but it really is not very useful to us at this point. The more useful way is to use an acetylide anion. So we could start with this same halide. We did this in the problem just before. We could react this with an acetylide anion. This does the same type of SN2 substitution. And we've added 2 carbons. Now the exciting thing about this reaction is that we can in fact do this again. Okay, we use sodium amide, as the base, and then I'll just put R, let's say Cl, and we can add whatever or our choice of alkyl group to the other end. And so now we've built up maybe quite a long carbon chain, and we're now set to convert that alkyne into some other functional group in stage 2 of our synthesis. Before we get into the acetylide reactions further, let's just look at some ways to actually make alkynes. So we have 2 ways. They're both related, and they involve a double elimination reaction. If we start with either this geminal dihalide or this 1,2, where it's a 3,4 position, but this is called a vicinal dihalide. Vicinal means on adjacent carbons. If we start with either of those and we treat them with 2 equivalents of sodium amide, we get a double elimination reaction. The first step will eliminate. It's going to follow Markovnikov's rule. So it's going to go to the more stable internal part. We eliminate once, like this. So we take off 1 hydrogen and 1 chlorine. And then the reaction proceeds again to give the alkyne. All right, so in this case, we're just losing an H and a Cl again. And this only really works because we're using such a strong base. In the bottom example, we have an H here, and we have an H here. So we do the first elimination, and it likewise gives us the vinyl bromide. Okay, so we've removed, in this case, this H and this bromine, and then we do this again. It removes those 2, and again we get the same alkyne. So let's step back again. So we have that geminal dihalide. What could we make that from? Well, we could either make it from the same thing that we finished with, which seems kind of ridiculous just to start with something and go back to it, or we could actually make this from the terminal alkyne, right? So it would add HCl 2 times, right? Follow Markovnikov's rule to put the 2 chlorines at that position. We do the double elimination, and look, what we've done is migrate the alkyne from the end to the middle. So that's something could be useful. In the bottom case, what would we make this vicinal dibromide from? And we would make it from an alkene by adding bromine, Br2. So in this case, we're converting an alkene to an alkyne, and that might be useful as well. So I've already showed you this, I think. Maybe I got ahead of myself, but the way to make the actual acetylide anion is to treat it with a very strong base. This is sodium amide. All right, and if it does that, it deprotonates to form the conjugate base. It would have the sodium plus is just a spectator ion plus ammonia, which is the conjugate acid, right? And so this is what we want to use to do our SN2 substitution. Let's look at a few more examples. So in this case, we're starting with acetylene. We treat it with sodium amide or sodium amide, and followed by bromomethane. So in this case, we're just going to add a methyl group to one end of the alkyne. The next one, we follow the same. We're going to make this anion. It's going to do an SN2 substitution right here. So we get this. Here's what our nucleophile was, and we have 3 carbons attached here. So we've extended the carbon chain. What about the last one? So again, we could deprotonate. It would make the anion here. Can we do a substitution with this 2-chlorobutane? Well, no. So let's think about this, or let's analyze this situation. We have a very strong nucleophile, which is also a strong base. And we have a secondary alkyl halide. What's going to happen? SN2? No, probably not. In this case, probably what's going to happen is an E2 elimination. And what we're going to do, even though we deprotonated the alkyne, we're going to reprotonate it. And our other product is just going to be the alkene that came from this chlorobutane. All right, so in this case, the acetylide is acting as a base rather than a nucleophile. So one thing to keep in mind is that this type of acetylide SN2 substitution only works for methyl and primary alkyl halides. If we have secondary alkyl halides, we get E2. If we have tertiary, of course, they don't do SN2. It would give an E2 reaction as well. Here are a couple of synthesis problems. So in the top one, we want to start with this secondary alcohol, and we want to go to this ketone. In fact, after we've completed the next chapter, this will be a very easy thing to do, but right now it's not quite as easy. So what do we need to do? Well, the one way that we've seen to make a ketone is to make it by hydration of an alkyne. So let's do this in a retrosynthetic way first. So we could go to either of two alkynes, right? We could go to this alkyne or this alkyne. Okay, either of those with acid-catalyzed hydration will give us that ketone. Okay, so do we have a sense for which one of those would be better? Well, we have to get back to that secondary alcohol. So let's see, how could we do that? Well, let's try this one. Okay, we can get to that from, amongst other things, this vicinal dibromide. We can get to that from this alkene, and we get to there by a dehydration reaction. All right, if we want to use the other, this one, the other alkyne, we would need to carry back through the same reactions and know how to make or how to dehydrate to the less substituted side, and we don't actually know how to do that. All right, so that one's not going to be as useful for us. This one's not as good at this point. All right, so let's think about this in the forward direction. Okay, we go from the secondary alcohol down to here. All we really need is an acid like sulfuric acid. Remember, it protonates the alcohol to make a good leaving group, does probably an E1 elimination to form the trans most stable alkene. We then want to convert the alkene into the dibromo compound. All we need to do is use Br2. We then use the reaction we learned about earlier in this video. We use sodium amide 2 times, right? And then from there over to here, we just need to use water and sulfuric acid. All right, so now we've done that. How many reactions do we have? 1, 2, 3, 4 reactions is the length of our synthesis. All right, what about the bottom one? We're again now going from acetylene to that tetrachloro compound. So let's do retrosynthesis. This isn't too bad. Only way we could get 4 chlorines on at once is to start with an alkyne and add chlorine 2 times. All right? So this would be for going back the other way, kind of doing the synthesis and retrosynthesis at the same time. So now we need to get from this alkyne, this internal alkyne, to just acetylene up here. So we're going to have 2 separate steps. It doesn't matter which order we do these in. We could go back to this alkyne and then back to that one. So to do these in the forward direction, we would add sodium amide followed by ethyl or chloroethane or bromoethane. We then need to add a methyl group, so same thing. Let's try iodomethane. And then we add our chlorine, and we get to the product. All right, so in these types of problems, you can do them retrosynthesis to figure them out. You can do them forward, depending on what you can see. What these type of problems do is help you to use your reactions. They can be good ways to practice and remember your reactions.